Okay, let's start class. Last time we started the generalized linear models. I think today we can finish the chapter 3. So the exam 1 will cover the chapter 1, 2, and 3 in the textbook, and that will be next Monday. And I've already posted in the Moodle, so we can talk about that after we finish today's material. Okay. Okay, so I think we stopped here. So last time we started to have a brief introduction to the generalized linear models, and we talk about for the binary response, we can have a few link functions. So we have 3 components for the generalized linear model. The first one is the random component that describes the distribution for the response. We can have the y follows a normal distribution. We can have like the binomial distributions. We have a multinomial distributions. We can have a Poisson distributions, and we can have some others like the negative binomials. But all these distributions need to have some general form, and this form is called exponential family, exponential distribution family. Okay, so the reason we need to have this all the distribution belongs to that family is that so that we can have a general formula to do the inference and the general algorithm. We can use the unified algorithm to find out the estimate of the parameters for all these generalized linear models. Okay, and we talk about the binary case. So for the binary case, we can have a few link functions, and we only talk about 3 here, but there are some others. The 3 that we talk about is first is the identity link. Identity link for the binary response is just to model the probability of having the y equals to 1 using a linear function of x. So that's the linear model approach. And the second is the logit link. So instead of using to estimate, to model the probability, we model the log odds. Why? Because this model has some problem. The problem is it's possible because we know that the probability, the left-hand side, has to be bounded by 0 and 1, right? But for the right-hand side, it doesn't have to be 0. So sometimes it could be below 0, or sometimes it can be beyond 1. So that's the drawback for using this approach. Okay, so using the log odds, that's the logit link, that we can solve this problem because what is the range for the odds? The range for the odds is we can have the smallest we can take is 0, right? When the pi x is 0. But upper bound goes to infinite, right? And that happens when the pi x converges to the 1. We know the odds goes to infinite, right? So when we take the log on this, then the range for the log odds becomes what? From negative infinity to the positive infinity. So that is a good range so that we can model this by the linear function of x. So we won't have any problem for this case. And for the probit link, same thing, because the probit link is using the inverse of the standard normal cumulative density functions. So basically, the probit link is model the z-score through the linear function of x, right? So what's the range of the z-score? The z-score ranged from negative infinite to the positive infinite, right? So we won't have that problem. So these are the three, but there were others like the log link and some others. So these are the three commonly used link function. And the one thing is, actually one student asked me after class is, for this one, when we use the identity link, is that the same solution as the OLS? What do you think? So for the linear probability model, can we just use the OLS? Because we have the y is 0 or 1, right? And we have x. So we can model the y through the alpha plus beta. Can we do that? No, we cannot. It's actually this linear model approach is, you can see the solution here. If you fit an OLS using the value of y directly, it will be slightly different. It will be close, but it will not be exactly the same. And you may ask why. The main reason is for the OLS. We assume actually the OLS, first OLS used the least square approach. And here, all these methods that we talk about using the GLM, that's using the maximum likelihood approach. And there is an equivalence between the MLE, maximum likelihood approach, and the OLS when the Y follows a normal distribution. Okay, but here Y is not following a normal distribution. Look at the family. It is binomial. So we are actually, when we solve this, we are using the maximum likelihood approach and assuming the Y follows a binomial. It's not normal. So if you use OLS, the solution will be different. But it won't be too different. It should be close in some way, but it's not exactly the same. Okay, so just be clear. So this is not the OLS solution. This is the linear probability model using the identity link for the binomial response. And we assume the Y follows a binomial, not normal distribution. Okay, if we assume the Y is normal and using an identity link, that is OLS. So that will have the same solution for the beta. Okay, but here is not. And we talk about this for the probit model. We also talk about, so that's where we start. Okay, so for the Poisson distribution, this is the PMF function for the Poisson distributions. Okay, so Poisson distribution is a common distribution that we use to model the counts. Okay, in other words, what is the range for the y? The range for the y for the Poisson distribution is the lowest it can take is 0. Then it's 1, 2 until infinite. So y is an integer, start with 0. That's the valid range for the Poisson model. Okay, and the probability of getting the y equals to a certain value is equals to the exponential of negative mu. So for the Poisson model, we have only one parameter, that is mu. Okay, and we will talk about what is mu in a minute. So E exponential to the negative mu times mu to the power of y. That's the value we take for y equals to that value, and over the y y factorial. So this is the PMF, probability mass function for the Poisson model. Okay, and what is that parameter? Mu. This mu is the expected value for the y. So here the mu is actually the expected value of y. Okay, and in the Poisson model, we can prove that mu is also equivalent to what? The variance of y. So you can see here in the Poisson model, we only have one parameter. And that parameter describes the mean and the variance. So this is the feature for the Poisson model. For the Poisson model, we assume the y and the variance should be the same. Okay? In other words, if the mu changes, if the mean changes, the variance will also change. If mu increases, the variance increases. Okay? So let's see an example. So suppose at a particular part on highway I-10, we know the average fatality accident is 2 per week. Okay, so we have 2 fatal accidents in that particular part of I-10 each week. So that is the expected number. Okay, so what is the probability of getting no fatal accident on this part of highway? So then the probability of y equals to 0, right, is equals to the e to the power of what? -2. Why? Because the expected number is 2, right? So e to the -2 times 2 to the 0, because we want to find out the y equals to 0, over 0 explanation. So that will be so this is defined by 1, okay? So we have e to the -2. So that is 0.135. So that's 13.5% of chance to get no fatal accident on this I-10 that week. Okay? And what about not just 1 week? Now we want to know over 2 weeks. So for the if over 2 weeks, what is that Poisson model? First is the average fatality will be what? It's not mu. Mu is just for 1 week. Is that right? If we have 2 weeks, it will be the mu times t. Okay, mu times t. Right? And mu is equals to 2. So that becomes 2 times t. Is that clear? So let's say, what is the distribution for the fatalities on this I-10 over not 1 week, but 3 weeks? Okay, then the mu equals to what? Mu equals to 6, not 2. Okay, so the probability of getting no accident, no fatal accidents over 2 weeks, over 6 weeks is what? Is the probability of y equals to 0 equals to e to the negative, not 2 anymore, but 6, because that's 3 weeks. So the 3 weeks, the expected number of fatality is 6. Okay, times 6 to the power of 0, 6 explanation. So that will be e to the negative 6. So that will be 0.002, which is much smaller than 0.135. Okay, so that's how we calculate the number of fatalities over not 1 week, but 3 weeks. Okay, and what is the chance of getting 6 fatal accidents over 6 weeks? And that is e to the negative 6 times 6 to the power of 6 over 6 factorial. So that will be 0.161. Okay, and you can see in the bottom we have a plot. So this shade with the this direction shade So this shows the expected fatality is 2. Okay, so for the expected fatality is 2, you can see the distribution goes that way, right? That's for the Poisson with mu is 2. But if the Poisson is mu is 6 over 3 weeks, so that follows this shape. Okay, so you can see different mu's gives different shape for the Poisson. Okay, so if we want to model the mu's using the Poisson distribution, so the random component is Poisson distribution, right? And we want to model the mu's through the Poisson distribution. So here we can have a few choice for the link functions. One is the identity link. So identity link means that we just model the mu directly through the alpha plus beta x. Okay, so that's the identity link. So directly model the expected counts using the linear function of x. And the second one is the log link. And log link is the most commonly used. And that is also the canonical link for the Poisson models. Okay, so log link is to model the log mu using the linear function of x. And we will compare these in a minute. And there are some other choice like the square root link function. So model the square root of mu over the linear function of x. Okay, but the most commonly used one is the log link. And that's also called the Poisson log linear model. Okay, so for the log link, let's see if x increased by 1, let's say if x increased from x to the x plus 1. So what is the difference for the model? Let's see. Let's say if mu x is e to the alpha plus beta x, right? So that's the log linear model. Is that right? Because here you can see if we model the log mu as this, so that is equivalent to what? That is equivalent to we model the mu through the exponential for the alpha plus beta x. Is that right? Because the log and exponential, these are the inverse, right, functions, okay? So mu x equals to that. And we can write out as exponential of alpha times exponential beta to the power of x, right? I'm just rewrite this as the product of these two, right? Okay, these are just very simple math. Okay, now this time we have x plus 1. What if x is increased by 1 unit? Okay, so that will be what? E to the power of alpha plus beta x. Why we have an extra beta? Because now this time we have x plus 1 instead of x. So we have an extra beta, is that right? So we have so that we can also write in this way, but this time we have an extra beta here. So we have the e beta, e to the power of beta times the mu x. What is mu x? Mu x is this one, right? So you can see what is the effect of beta in the log linear model. So the effect of the beta is what? So that means by 1 unit increase of x, the expected counts is increased by what? E to the power of beta. And that's how we interpret the slope. Okay, and we will see some examples in a minute. And here, what if beta equals to 0? If beta is 0, that means what? E to the power of beta is 1. Is that right? So that means mu x plus 1 and mu x are the same. So in other words, mu is a constant function of x. So this is mu is a constant function of x. Because if x changes, the mu x is the same. It's a constant. Is that right? If beta is positive, then that means when we have a 1 unit increase in x, the expected counts will also increase. And the increase rate is e to the power of beta. And when the beta is less than 0, that means e beta will be what? If beta is less than 0, e beta will be less than 1. So that means by 1 unit increase in the x, the expected counts will actually decreasing, right? So that's how we interpret the model, and also that's the effect of beta on the Poisson log linear models. Okay, now let's see an example. So this is a horseshoe crab example. In this study, we have 173 samples. The response is the number of satellite. So what is the satellite? Satellite are the number of male crabs that is around a female crab. Okay, and that is called a satellite. And the number here, we collected 173 female crab and counted their number of satellite around these 173 female crabs. Okay, and we want to model the number of satellites around the female crab through some features for the female crabs. For example, one is the female's color. We have light, medium, and dark and medium. And the fourth one is dark. Okay, why the color? Because the female crab's color is related to the female crab's age. Okay, and the spine condition. Okay, for the spine condition, we have both good, one bad, and both bad. Okay, so for the crab, we have the carapace on the back, right? So the spine is just these two parts. So they are both good or one bad or both bad. And the weight of the crab, that is the weight. And also the carapace width. Okay, so that shows the physical size for the female crab. Okay, so all these the weight and the carapace width, these two are the numeric, right? And for the spine and the female colors, these are categorical. But for the spine conditions and these, we do have some order information here. Okay. For the carapace width, we can group them into 8 groups. Okay, so the smallest is less than or equals to 23.25 centimeters. And this is second and so on. The largest group is over 29.25 centimeters. Okay, so we have the average width and standard deviation for the carapace width is 26.3 and 2.1 centimeters. So this is the data set. Now let's first just consider we will use this data set a few times, but here we only consider to model the number of satellites through the carapace width. Okay, so in this plot, you can see we have 8 dots in the plot. So these 8 dots shows the average width and the corresponding average number of satellites for each of the 8 groups. Okay, for each of the 8 groups. You see here we group the carapace width into 8 groups. Okay, so for each group, we found the samples and get the average number of satellites and also the average carapace width for each group. Okay, so we have this information and we do the dots for each group. So we have 8 dots, 1 for each group. Okay, and you can see here, if you see the trend, you can see there seems to be a linear trend between the carapace width and the number of satellites. In other words, if the carapace width is larger, then it tends to attract more male crabs near the female crab's nest. Okay, so that's is based on the data that we see. So there's a linear trend. So that motivated us to first fit a Poisson regression model with identity link function. Why? Using the identity, because from this plot we see the width and the number of satellites have a linear relationship. Okay, so that's why we can just try the identity link to model the mu directly using the linear function of x. Okay, so that's the identity link, and we can get the model is the intercept is negative 11.5 and the slope for the x is 0.55. Okay, what does that mean? That means by how do we interpret the slope? You can see by 1 unit increase of x. In other words, if the carapace width is increased by 1 centimeter, okay, the expected number of satellites will what? Will increase by 0.55. Is that right? Or we can interpret in a better way is not 1 unit increase, but 2 centimeters. Okay, if we have 2 centimeters increase in the carapace, so the expected number of satellites will be increased by what? By this multiplied by 2, so that will be 1.1. So that will be by about 2 centimeter increase in the width corresponds to about an extra satellite. So that is how we interpret the slope using the identity link. Okay, so that's the identity link model. And we can also fit a different link function. Let's try the log link. That's the most commonly used. Okay, so compare the log link and the identity link. You can see the majority part around the data range, they are very close. But for the log link, it's a nonlinear function between the width and the expected number of satellites. Okay. Now let's see in the R. So this data set is in this website. You can download it. And here I fit a log linear model. So that is using the GLM function, but the family is Poisson with the link is log. Okay, and this is the Poisson model with identity link. Okay, so still the family is Poisson, but the link is identity. Okay, so this one we've already seen the model. That's intercept, that's the width. But for the log linear model, we model the log of mu through the linear function. So in that case, the intercept is this one, slope is this one. Okay, so this is the log linear model for the horseshoe crab example. And how do we interpret it? Okay, so here, remember the way we interpret the log linear model is by 1 unit increase in x, the mu will increase by a factor of what? Exponential to the power of beta, exponential beta, right? So here, the beta is 0.164. Is that right? So that means the exponential of 0.164 is what? And that will be, the exponential of 164 will be 1.18. So that is 1.18. So what does that mean? That means by 1 unit increase of x, the expected counts will increase by what? Will increase by about 18% in the number of satellites. Does that make sense? Because now the mu hat for x plus 1 is 18% increase of the mu at x equals to x. Okay, so that means by 1 unit increase of x, the mu will be increased by 18%. So you can see for the log linear model, the x effect is multiplicative. Okay, but for the identity model, it is additive. Because this one unit increase, 1 centimeter increase in width gives 18% increase. Okay, so that is multiplicative. But for the identity link, you can see 1 unit in 1 centimeter increase will correspond to about half of a satellite, or 2 centimeter correspond to 1 extra satellite. So that's additive. So that's the difference between using the identity and using the log link. Okay, and for this log linear model, you can see we have the standard error, right? Standard error for the intercept and slope, and we can do the inference. Okay, for the standard error of the width, it's about 0.02, right? So the z-score is about 8.2, which is much bigger than 0. So that means the beta hat is significantly greater than 0. So that means the data have a strongly support that there is a so when the width is increasing, the number of satellites is significantly increasing. Okay, and this beta hat is obviously significantly different from 0. Okay. Okay. So now let's see, there is a common problem for using the Poisson regression. And that problem is called over dispersion. Okay. So let's look at, we have the 8 groups for the width, right? So these are the number of cases falls into each group. Okay. And this is the number of satellites. And this is the sample mean. And this is the sample variance based on the 8 groups of width. And you can see the sample mean and the sample variance at each levels, at each group. You can see they are not the same, right? So obviously the mean and the variance are not the same. and the variance actually is greater than mean in all the groups, right? So that problem is called over-dispersion problem in the Poisson regression. And you may ask why this over-dispersion happens. Because for the Poisson model, under the assumption, the mean and the variance should be the same, because that's the feature for the Poisson model, right? But here they are not. Okay, and that is called over-dispersion. And the common cause for over-dispersion is the heterogeneity among the samples. What does that mean? That means it's not so the carapace width is not the only factor, that affects the number of satellites. And there are several others. Factors can affect that. For example, like the weight, color, and the spine conditions. So these may also affect the number of satellites. And here, since we only focus on the width and ignore the other relevant variables that will affect the number of satellites, so that means that the data is heterogeneous. That means within each group, although we have this group, right, which has the carapace width is less than 23.2, but that includes different members with different values for other relevant variables. Okay, for example, we have 14 cases in the first group, and these 14 cases may have different colors, different weights, and different spine conditions, and that they all may affect the number of satellites. Okay, so in that case, we usually will observe the over-dispersion because there were too many other relevant variables which we ignored, which we didn't consider in the model. So that's why we have an over-dispersion. If we add all the relevant model in relevant variables into the model, then assuming the Poisson model is a good model, then the mean and sample variance will be very close. Okay, so that's the common cause for the over-dispersion, is because of the heterogeneity among the subjects that we didn't include other relevant variables in the model. So if we have an over-dispersion problem, what should we do? Okay, the first one is we should consider other variables into the model. For example, we should include not just the width, but also the weight, color, and the spine condition into the model. And that may relieve the over-dispersion problem because now we have more variables. Okay, so that's one way to handle the over-dispersion. If we have other relevant variables information, we could include these into the model. Okay, and that's one way. Another possible approach to handle the over-dispersion is to use a more flexible model. So here, the Poisson model is very rigid. Why? Why I said rigid? Because Poisson model has only one parameter. And that limited the mean and the variance to be the same. Okay, is there a possible distribution that we can use that can relax this constraint between the mean and the variance? Can we? Yes, there is one that we commonly use. That's called a negative binomial. Okay, so negative binomial regression can be used for the over dispersion problems to handle the over-dispersion problems. Okay, so the negative binomial distribution is a discrete probability distribution like the binomial, but it's negative binomial. Why it's called a negative binomial? Because it models the number of failures in a sequence of independent and identical distributed Bernoulli trials before we reached a specified number of success. Okay, so here, let's say for the negative binomial, we have two parameters. The first one is P. This one is the same as the binomial distribution. That's the probability of being success, or the probability of having y equals to 1 for each trial. Okay, and each trial follows a Bernoulli. Okay, and it's IID. IID means for each trial, they have the same P. They have the same probability to getting y equals to 1. And they are independent. Okay, and there's another parameter that is the number of success, and that has to be pre-specified. Okay, so let's say P is a certain value, that's the probability of being success, and R, let's say, is 2. So the number of failures that we need to have before we get to success with the probability of being success for each trial is P. And that distribution follows a negative binomial distribution. Okay, so that's the number of failures we will get. The probability of getting X failures before we get R success. And with each trial has the P in probability of being success. Okay, and that is equivalent to the X plus R minus 1 choose X times 1 minus P to the power of X and the P to the power of Y, R. Okay, so that's the negative binomial. For the negative binomial, how many parameters do we have? So we have 2 parameters, P and R. For the Poisson, we only have 1. So that's why negative binomial is more flexible than the Poisson, because we have 1 extra parameter. And that allows the mean and the variance to be different. So the mean is this one, variance is this one. So you can see they can be different. And often we can rewrite these mean and variance through a different way, through the expected value of y equals to mu. So the mean we can write as mu, but we can write the variance as mu plus d times mu squared. Okay, so we can write the variance in this way. And in this, if we rewrite it through here, then you can see there is a factor called dispersion parameter D that describes the variance. Okay, so the variance is the mu plus the dispersion parameter D times the square of the mean. So you can see the negative binomial does not require the mean and the variance to be the same. But when the D converges to 0, then you can see the mu and the variance are going to be the same. Okay, and that is a special case. So you can see then for the D goes to 0, the negative binomial distribution converges to a Poisson. So in other words, Poisson distribution is a special case for the negative binomial with D equals to 0. But negative binomial is more flexible than that. Okay, than the Poisson. So in R, there are many ways to fit the negative binomial. Okay, so here I'm just using a function called the GLM.MB. That is a function in the library math to do the negative binomial. Okay, and that's the number of satellites over the width, the crab data set. So you can see for the negative binomial model, we have the intercept and the width is this. The corresponding standard error for the intercept and width is this, and we have the z values and p values. Okay, so they are both highly significant. So for the negative binomial, we have this model. Okay, and in the model output, there is a parameter called theta equals to 0.9. So what does theta mean? So theta is 1 over of the dispersion parameter d. Okay, so theta is 0.905. That means the d is equals to what? D is equals to 1 over theta. Is that right? So that's 1 over 0.905. And that gives 1.1. So in other words, for the negative binomial, okay, at a particular level of mu hat, the expected variance is roughly equals to what? Mu hat plus the mu hat square, right? Okay, so that is different from the mean and variance are the same. They both equals to mu in the Poisson. Okay, and the fitted value, if you compare the fitted value for the intercept and width using the negative binomial and using the Poisson distribution, you can see these are very close. They are quite close. Okay, one is negative 3.3, 0.16, but you can see this is negative 4 and 0.19. So they are very close. Okay, but if you look at the standard error, okay, let's just look at the standard error for the width. That's 0.044. But what about this one? 0.0199. So which one is smaller? This one is smaller. This is about 0.02, right? So this is for the Poisson model, it's 0.02 for the standard error. But for the negative binomial, it's 0.04. Okay, so if we use the 95% word confidence interval, okay, so that is the point estimate plus minus 1.96 times the standard error. Okay, so for the Poisson model, it's this one, but for the negative binomial, it's this one. So which one is wider? Negative binomial is wider. And this shows what? Shows for the Poisson GLM, the confidence interval is unrealistically narrow. That is because it does not allow the overdispersion. But if we allowed overdispersion in the negative binomial, it is more flexible and it shows the confidence interval is much wider. Okay? Okay, so for the count regression, there is a special case which also commonly used in reality, and that is when the events occurs over time, space, or some other index of size. And instead of modeling the counts, people find it's much makes sense to model the rate because the counts depends on two factors. One is the rate, one is the size. Okay, for example, if we are analyzing, let's say, the number of a certain crime, like murder, from different cities. Okay, so if we just model the number of murderer over a certain time period for that particular city, okay, and that is only meaningful for this particular city. Why? Because we know that the number of murder or the number of crimes depends on the population for that city. If that city has a small population, of course, the number of crimes will be slower. If we have a large city with large populations, of course, the number of crime will be higher. So this depends on the size of the city, the population or size, right? So instead of modeling the counts, we model the rate. That means we can model the number of murderers among, let's say, 100,000 people. Okay, so that's a rate to model the rate instead of the count. So when a response count Y has index such as the population size equals to a certain value, let's say we use T, then the sample rate is Y over T. That's the rate. Okay, this is the count, Y is the count, Y over T is the rate. Okay, so the expected value for the rate is mu over T. Okay, when we modeled a log linear model for the expected rate, then we have the log of mu over T equals to a linear function of X. And that can be rewritten on the on the left-hand side to be the log mu minus log T. Is that right? So that is to model the rate. And then we have this adjustment term. That's the negative log T. And we can also put it into the right-hand side. Then that will be the what? The log mu to model the log mu with a linear function of X. Is that right? Then plus the log T. Okay, on the right-hand side. And this log T has a name called offset. Okay, so the mu is proportional to the index of T with the proportionality constant depend on the value of the explanatory variable. Okay, so that's the rate model. So let's see an example. In this example, the response is the collision between the train and the road vehicles in the United Kingdom in 1975 to 2003. And the purpose is to find out the time trend for the train road vehicle collision in the UK. Okay, and the explanatory variable to be used here is the number of years since 1975. And the offset is what? Think about the number of collisions between the train and the road vehicle. And that should be directly related to what? To the travel length, right? So here the offset is the millions kilometers of annual train travel. Because if the train travels longer, of course, the chance of having a collision between the train and the road vehicle also increases, right? So we need to adjust the using the rate instead, okay? So we can using the rate model. So the left-hand side is the log mu over T. So that's the using the log link, right? And for the rate, okay? And that is modeled by a linear function of X, okay? And that's intercept, and that's the slope, and X is the indicator for the is the year, okay? But here we set the 1975 as 0. Okay, so start with, so X is the number of years from a number of years after 1975. Okay, so 1975 corresponds to the X is 0. And we have the data from 1975 to 2003. For 2003, the X is 28. That's 28 years after the 1975. Okay, so based on the fitted model in this fitted rate model, and you can see how to fit a rate model in R. You can use the GLM functions, but here the data and this data set is in a library called NDHGLM. That library has the data set called train. Okay, if you want to play with this data set, you can download this library in the R and then open it. And then we can use the GLM functions with the Y is the number of collisions between the trains and the road vehicles. And X is the year, number of years after 1975. But here we need to, because this is a rate model have an offset. That's the log T, right? So here the offset is what? Log T. Okay, and so the T is the millions kilometers annual train travels. Okay, so the family is Poisson because the Y follows a Poisson distribution, right? And the link is the log. Is that clear? So that's the rate model. Okay, and you can see that's the estimated intercept and the slope. Okay, so how can we interpret the slope? So you can see the slope is negative 0.0329. Okay, so you can see that means what? When the x is 0, that is 1975, the estimated rate for the train accident is 0.0149. Okay, I just plug in the x is 0, so that actually gives us the rate. And here, this is actually equivalent to what? To this one, take the exponential. So that's the exponential of negative 4.211. Okay? So that is the estimated rate, okay, for the 1975. But in 2003, what is the estimated rate? The estimated rate is exponential negative 4.2 plus the slope is what? I'm sorry, not plus. It should be minus because the slope is negative. Minus 0.33 times. So for the 2003, the x is 28. That's 28th year after 1975. So that is equals to 0.0059. Okay, so you can see compare with these two numbers, the difference is about 0.00 yeah, so the difference is 0.008, right? Okay, so the difference, so we can say by after 28 years, the drop is about 0.008 per million miles, or 8 per billion kilometer, 8 per billion kilometer. That's the drop. That's the difference. Okay, but the estimate at 2003 is 0.006. That's what we estimate for this year. This one is the difference between the 1975 and the 2000. Okay, so you can interpret through that. Okay, after we fit the generalized linear model, and we can also do the inference. Okay, and we can use the word test approach to do the confidence interval and also to do the hypothesis test. And we can also use the likelihood ratio test approach to estimate the confidence interval and to do the hypothesis test. Okay, so for the word test, that's very simple, very easy to use, because for the word test, you can see for the output, we have a standard error, right? For each parameter. Okay, so for the word test, we can just use the point estimate. That's the point estimate, plus minus the critical value, depends on the confidence coefficient. Let's say 95%, then it will be 1.96 times the standard error. Okay, and that will be the confidence interval based on the word approach. And we can also do the hypothesis test. The test we do is just to use the point estimate divided by the standard error. And that is the ratio showed here. And that under the assumption, this should follow approximately a standard normal. So this is the corresponding p-value. Okay, so that means intercept is highly different from zero, and that's obvious. And the slope is significantly different from zero. Okay, because of the z value and p-value are significant. Okay, so that's the word test approach. And also you can use the likelihood ratio test. Likelihood ratio test is more complicated. Okay, and we can do that through using the R's. Okay, so let's see the snoring and heart disease example. Okay, remember for the snoring and heart disease example, so this is the data set. Okay, so we have 4 levels: never, occasional, nearly every night, and every night. And we have the heart disease study. Okay, so here, this is the Y. We have the 0 and the 1s. That means 1 means heart disease, 0 means no heart disease, and X, we have 4 levels, 0, 2, 4, 5. These are the scores that I assigned to based on the snoring conditions. Okay, and here we can model the using the identity link, model the probability through the identity link. So that's the linear probability model. And the second is that's fit 1, and the fit 0 is the naive model with the snore coefficient equals to 0. So that is heart tilde 1. So that means only the intercept model without any coefficient for other variables. Okay, and then we can do the likelihood ratio test to test the snoring effect. Okay, so for the likelihood ratio test, what we can do is we fit these 2 models, fit 1 that includes the intercept and the snoring, fit the naive model only the intercept, and then we can use the ANOVA test. For the fit 0, that's the intercept only model, and fit 1, that's the identity link model. And we can do the test is chi-square, so that shows the likelihood ratio test to test the snoring effects, beta equals to 0 or not. And you can see that that's the p-value is different from the word test, slightly different from. And you can see the deviance is that, so the p-value is highly significant. So that means there is a significant snoring effects in the models. Okay, these 2 models are very different. So that shows the importance of including the snore, that variable. And we can also have a 95% likelihood ratio confidence interval using the conf_int function in the R. For the fit 1 includes the intercept and the snore variables. For the parameter is snore level is 0.95. So that gives 95% confidence interval for the snoring coefficient. And that's the confidence interval. You can see it's different. It should be different from the word confidence interval. Okay, and you may ask which one we should use. Okay, so the statistic inference based on the word test is simplest. That's the easiest to use, but the likelihood ratio based inference is much more trustworthy. So if you want to do some inference on the confidence interval hypothesis test, the best one is to choose is the likelihood ratio test. That's the one people usually use. But word test, you can still use it because it's very simple, easy to use, but there are many debates of using the word test results to do the inference because this is not as accurate as likelihood ratio test. Okay. Okay, so deviance is a very important concept in the generalized linear models. Okay, so what is a deviance? So deviance is the -2 log likelihood between the model that of interest and a model that is the most complicated model we can have. That's what we call a saturated model. Okay, so let's say S is a saturated model. That is the most complicated model we can have. And M is the model of interest. Okay, so the deviance is defined by the -2 times the LM, that's the likelihood, maximum likelihood value for the model of interest, and the maximum likelihood value for the saturated model. Okay, and their difference multiplied by -2. That's the deviance. So the deviance is a likelihood ratio statistic that compare the model of interest to the saturated model. Okay, and this can be used as a test statistic, although most of the time we don't use the deviance to do the test directly. Okay, but this could be used as a test statistic. That is, if we use that, that means we are testing all the parameters in the saturated model, but not in the model of interest equals to 0 or not. So if we do that, that is what it means. Okay, and we will see an example in a minute. But most of the time we use the deviance is for a different purpose, is to comparing the deviance of two models and then do the inference and do the model comparisons between these two models based on the deviance. Okay, so for the now let's see for the snoring and heart disease example. So here we can compare the linear probability model and the saturated models. Okay, so let's see, this is the data set, right? And we can fit a linear probability model, and we can also fit a logistic regression model, right? And what is a saturated model? So here, for both linear probability model and the logistic model, we use snore here. So we have 4 levels. Never is 0, occasionally is 2, nearly every night is 4, every night is 5. So these are the assigned scores for the 4 levels. Okay, so we fit the heart disease, the probability of getting the heart disease through these snoring levels. So I used scores here, right? And the saturated model is what? The saturated model is to model the heart disease rate through a factor of snow. So what is a factor of snow? So here, that means now we treated snow as a factor. Factor in the R means a categorical variable. So in other words, we don't have this 0, 2, 4, 5 relationship. We just modeled each level by its own heart disease rate. Okay, without assuming the relationship is 0, 2, 4, 5 anymore. So we modeled each level, snoring levels by its own heart rate, heart disease rate. Okay, so how many parameters do we have for the saturated model? It's not difficult to find, right? So we have 4 levels, 0, 2, 4, 5. So each level we modeled it. So we have 4 parameters used in this model. You may ask why 4? Because each level we modeled a heart rate, heart disease rate. So how many parameters? Of course, it's 4. Is that right? Each level we have 1. But how many parameters do we use for the linear probability model? 2. Is that right? Because we have 1 for the intercept, beta 0, and 1 for the slope, beta 1 for the snoring. Is that right? So how many parameters do we need? We have 2, beta 0 and beta 1. Is that right? And for the logistic model, we still use 2 parameters, beta 0 and beta 1. So you can see which model is more complicated. Of course, it's saturated model because that's the most complicated model we can have based on the data we have. We have snoring information, we have the disease information. We just fit each level by itself. We need 4 parameters. That's the most complicated we can have. Okay, so after that, we can find out the deviance. Okay, so here, and then we can do the test. Okay, so you can see the deviance for the linear probability model, that's fit 1 is what? So the deviance is 0.069191. Okay, so that's the deviance between the 2 models. That the first one is the linear probability model, and the second one is the saturated model. Okay, and we can run the chi-square test. The p-value is 0.966. And you may ask why this one is 0. So how do we get that p-value? Because the degrees of freedom is 2. Why is 2? Because as I said, for the saturated model, what is the degree of freedom? We have 4 parameters. Is that right? For this one, we have only 2 parameters. So what's the difference between 4 and 2? So that means the model of interest is having 2 fewer parameters compared to the saturated. Is that right? So that's why the difference is 2. So that's the difference of the number of parameters is the degree of freedom here. Okay, and the deviance is that, and that follows a chi-square distribution. So you go to the chi-square table and you can find that. Of course, if you use the tables that I give you, that should be a range. It's not exact number, but this is from the software. Of course, it will give you exact p-value, okay? And this one is getting the deviance for the logistic regression. That's 2.8. And still the degree of freedom is 2. P-value is not significant. So for both models, you can see the deviance and the corresponding p-value are not significant. So that means what? There's no significant difference between the saturated model and the model of interest. Okay, so then that tells us maybe we should just use the simple model, because no significant difference between a simple model and a more complicated model. That means if there's no significant difference, we always prefer the simple model, right? So that's the deviance, okay? And we can also use the deviance idea to compare two models. So here the deviance is to compare with the saturated model, right? So we want to compare this one with a saturated model. Then we can use the deviance directly. But a natural question is, what if now this time I want to compare model 1 and model 2, and none of them are saturated model? What should we do? Right? So we can still use the deviance. Why? Because you can see if we have two models, now let's say it's model 0 and model 1, okay? So both of them are not saturated model. So we can still do the likelihood ratio test. And the likelihood ratio test, the statistic is what? Is -2 log likelihood difference. So that's -2 times L1 or L0. That's the likelihood ratio, or that's the maximum likelihood value for the model 0 minus the maximum likelihood value for the model 1. And we can rewrite it as -2 L0 minus LS. What is LS? Look, what is LS? LS is the saturated model likelihood, maximum likelihood value. Okay, so we can rewrite it as this one minus this one. Can we? It's just a simple trick. We put the LS in twice, right? We subtract and plus. Okay, so so this is equivalent to this. And what is the first one? The first one is the deviance for model 0. Is that right? And what is the second part? Second part is the deviance for model 1. Is that right? So the difference between the deviance for model 0 and the deviance for the model 1 is the likelihood ratio test statistic that compares model 0 and model 1. You see that? So that is another use, which is the more commonly used. Okay, so this gives us an idea that we can compare the models, two models, based on the deviance. Okay, so this test statistic is large if model 0 fits poorly compared to the model 1. Okay, and this likelihood ratio test statistic follows an approximate chi-square distribution with the degree of freedom equals to the difference between the residual degree of freedom value for each model. Or we can calculate it in the difference of additional parameter in the M0, but not M, or in M1, but not in M0. And you may ask which one we should use. They're equivalent. Depends on your preference. You use one of them should be equivalent to the other one. If it's different, that means you must make some mistakes. Okay, so now let's see for the, so this is the, fit one is the linear probability model for the snoring example. And we use ANOVA to test its chi-square. So that gives the model comparisons for the no model and the model. The no model is the model with the intercept only, and the snoring, and that is the model that includes the snore variables. Okay, and you can see the difference is 1. Okay, and the deviance is 800. No, the deviance is the 65, I'm sorry. Okay, and the p-value is 4.9. So that means there is significant difference between the intercept-only model. The no model is the intercept-only model without snoring effect. Okay, the second model is the with the snoring information. You can see the p-value is highly significant. There's a big difference. And the deviance is 65. And this 65 is the difference between these two models. So the deviance for the no model is what? Deviance for the no model is from the 900. And this one is from 834. So the difference is 65. Okay, and the p-value is this one, with the degree of freedom is 1. Why is degree of freedom is 1? Because comparing the no model and the snoring model, you can see what is the number of additional parameter added. We only added one parameter. That's the snoring information. So that's why it's 1. And you can also use the degree of freedom for the residuals. You can see the degree of freedom for the residue is 2,483. And this is 2,482. So the difference is what? Difference is 1. You see that? So both approach gives you 1. Which one is easier to use? I would prefer the second one. Second one, you can easily see there's just one additional parameter added, right? But anyway, this is how we compare the models through the deviance. Okay, so I think we can stop here, and this is last slides, and I can do that next time. So is this a calculation? So I'm not sure what type of calculation you are talking about. I think for those part that's, if it can be done through the calculators, yes. If we cannot do that through the calculators, like to find out these estimates, of course, I won't test you, right? But I can give you this information, and I can ask you to, like, I can give you the deviance, the residual deviance, and you should be able to find out the degree of freedom and then do the chi-square test. Yes, that is doable through the calculators. And for the exam 1, I posted, see, in the Moodles, so just in case if you didn't see, so that will be on next Monday, 10:30 to 11:50 in class room 44, Wooling Hall. That is in the basement, not on the first floor. Okay, so you have to go down to the basement, and the exam covers the chapter 1 through 3, and it will be closed notes, books, and calculators, and I will provide the tables for the chi-square and the standard normal distributions. So you don't have to bring the tables. And the tables I've already included in the here, in the general information here, you have the statistic table. So I will use these tables. So, and you can bring a calculators and a piece of A4 size paper as your formula sheet. You can write both sides. Okay. Yeah. Okay. Any questions? Okay. So if you don't have any questions, let's stop here.